And now we have sort of hardcore session with configuration files and so on and so on. So please welcome our next speaker, Levkin, who will tell us something about securing Kubernetes. Please welcome.
One, two, three, sound check. Seems good. Hello, guys. Really joyful to see so many faces curious about Kubernetes security. I hope you bring no tomatoes in the pockets. My name is Roma. I work at Exness. Well, it was working a minute ago. I work at Exness as a security engineer responsible mainly for various platform and Kubernetes stuff. Of course, I don't believe that I know this Kung Fu as good as Neo. But what I do believe in is that securing Kubernetes is not yet a practice backed by really established set of technologies, nor by really established set of mature processes, which makes me believe that we should share information regarding the technologies themselves, and of course about the stories, how we were implementing those technologies. Why this particular topic? Well, let me start from afar. Securing Kubernetes means that you use all the same, let's call them traditional security controls. I mean, network and runtime security, secrets management, vulnerability management, access control. I mean, you are familiar with them. They have a proven record of being helpful to secure your infrastructure. But with admission control, Kubernetes brings something really fresh to the stage, mainly because of the idea that it can be used not only as a separate control, but as a control over other controls as well. And this is probably the main idea of my talk. The agenda presumes we have a quick recap on how Kubernetes admission control works. Then I will try to attract some interest to this technology, following by the story of how we have been using this control at Exness. So let's move on, starting with recap. When I said that Kubernetes brings something really fresh, I deliberately didn't use the word new, because in fact there is nothing new. Regarding networking, we have a network access control or posture management. It is when a device is not permitted to the network unless it fulfills some predefined requirements. Another example is an incoming HTTP request is dropped by a web application firewall in case it contains an extra quotation mark. I mean, the idea is quite simple. We have some technical opportunity to analyze and inspect the object before accepting or admitting this object to our infrastructure. But Kubernetes is the system where admission control really shines because of the way how Kubernetes works. And I mean the declarative model here. This model presumes that you have some intended state of the service even before the service is running. These kind of systems presume that you don't execute a chain of commands to achieve the state. You just submit a declaration of the state or description of the state. And the system then executes everything needed to achieve the state under the hood. These kind of systems are quite reliable against unexpected events. In case of Kubernetes, if we have a node failure, we know that the pods should be rescheduled across the healthy nodes. But as a security guy, I see a great potential here as well, because what is the main outcome? The main outcome is that we have the initial state even before the service is running, which means we can apply some analysis and some inspection on this state. And it is relevant not only to workloads. I mean, not only pods, daemon sets, and replica sets can be expected, but any kind of objects like roles, role bindings, network policies, limit ranges. I believe you got the idea. And this mechanism is native. On the slide, you can see the standard handling chain of incoming requests. After passing some initial steps like authentication and authorization, request will sooner or later reach firstly the mutating admission and then validating admission. These are the names of the processes. These processes are backed by so-called admission controllers. An admission controller is a piece of code that, as you might guess, either change a request according to some predefined rules or just validate the request. In case of success, the object that the request carries is then created in the cluster. In case of failure, of course, it is dropped, in most cases with some reason why it was dropped. There is a list of compiled-in admission controllers, meaning that they are in place out of the box. Some of them are quite transparent for end users and needed to internal operations mostly, but some of them are quite handy and they can be used to significantly enhance your Kubernetes operations, like the limit range admission controller, which you can use to insert default resource requests to your pods in case your pods do not have them by default. Nothing stops you to bring your own admission controllers. Sometimes they're referenced as custom admission controllers, sometimes as admission webhooks. And in the field of information security, we have a term policy engines. The idea remains the same, the logic remains the same, but in this case, you should explicitly install additional software to your cluster. On the slide, you see a part of so-called admission request. This is the main source of information for admission controllers, and it is kind of wrapping on the incoming request. Technically, this admission request consists of a detailed information about the object that the request carries and some contextual data, like the information about the user who submitted the request, the type of operation, and so on. Important note here, this is the main source of information for your admission decisions, and we will have this information a bit later. Another structure called webhook configuration. This is something that defines for what kind of resources and for what kind of operations our incoming request should be wrapped with an admission request structure, like we saw on the previous slide, and to be sent to the webhooks that are registered inside the webhook list, inside the same webhook configuration. Important note here that it is not possible to use admission control for read-only operations. For any kind of other operations, including custom verbs, it is possible. You can place get list and watch in the list of operation, but it will take no effect. So bear that in mind. If you take something similar to a production-ready cluster, you will not be surprised to see some of these titles installed there. And they bring their own admission webhooks. For example, if you use Istio, there is an object called Istio Gateway. It is somewhat similar to the native ingress object. And when installing Istio, you provide an installation of an Istio webhook. If you try to create an Istio Gateway with no mandatory section called host section, the attempt will be failed. And the Istio admission webhook will tell you, sorry, I think this manifest is invalid. Please put the needed sections in the manifest. So this is an example of how you already use admission control, even if you didn't notice that you have been using it. So quite a narrow case just to check the conformance of custom resources that these titles usually rely on. On the contrary, guys on the right, these are referenced as policy agents, and they enable you to create general policies, which you can use to implement almost limitless logic, almost limitless inspection logic for any kind of resources, including custom resources, including native resources. And during the next chapter of my talk, we will explore some reasons why you want to bring these guys to your clusters. And a quick note here, I do not want to sell you either of these solutions, but since we rely on both of them at Exness, sometimes I will be referring to some specific, like code samples. But again, I tried my best to speak about general concepts rather than about technical implementation. So these concepts should be fine no matter of the tool set of your choice. Thanks to Artem and his great talk on the containers and Kubernetes threat landscape. For those who were not present, on the slide you can see the Kubernetes threat matrix made by Microsoft, and it tries to resemble the famous MITRE attack and techniques matrix. So the idea is that we see the different techniques of attacks against Kubernetes grouped by some common stages of a modern cyber attack, starting from an initial access up to delivering an impact. I do not expect you reading all these small letters at the moment. You could do so later when downloading the slide deck. Just to show you the big picture, more than half of the threats can be resolved using admission control. I took green color and put on the threads that can be fully remediated using admission control. And as you might guess, green means that the thread can be remediated partially, or where admission control can be used to assess other control to fully remediate the thread. And I was quite strict to myself when placing these colors. For example, if we take this application vulnerability and application exploit threads, of course, we understand that admission control is not a magic tool that will rewrite your vulnerable code. But it is a tool that you can use to enforce some security best practices. For example, dropping all Linux capabilities, thus eliminating the possibility to the vulnerability to be exploited. So should I put yellow color here? Well, I decided to not to do so. Some magic happens with this clicker, really. Regarding the green cells, this is the point when I say that admission control is a separate control. The green cells are addressed mainly by the famous pod security standards. I believe most of you are familiar with the concept of pod security policies. They are now deprecated, they are replaced by pod security standards, and there are admission controllers with the same names, but I want to talk not about the admission controllers themselves, but about the settings themselves. I believe you are familiar with them. Try to avoid running your containers as root users, try to avoid using host path volumes, do not allow privilege escalation. I really believe I don't need to spend time to explain you why these settings are proven to be the security practices. What I want to highlight here is that this is a must and the first step of implementing a proper admission control in your clusters. This is the first line of defense when your application is already compromised. And I would be happy to say that this is the 20% of the work that will solve the 80% of your potential security problems. But unfortunately, it's not true. It's not just 20%. It's much higher. And more details will be provided during the next chapter of my talk, where I will describe how we have been implementing this and what are our outcomes and experience. But again, this is the core of admission control when we say that it is a separate control. Let's better spend some time looking at how admission control can be used to patch other controls, starting from role-based access control. It is a native mechanism of Kubernetes to establish an access control for your clusters. And it is quite limited in nature. For example, it doesn't provide you with deny rules. Only additive logic can be used. Another example, it cannot use regular expressions or even wildcards in access control rules. But we can use admission control to try to fulfill these gaps. Remember that we have this user information section in our admission request. And if we have a proper combination of this user information and different parameters of the object our request carries, we can try to combine those parts to try to achieve deny rules, for example. A scenario from the wild. Let's say we have two teams, site reliability team and security team. By default, they have read-only access cluster-wide. And we use a combination of cluster role plus cluster role binding, meaning that we grant access to all namespaces in the clusters. In case of firefighting, we want to provide additional permissions to be able to get shell into a problem container, executing the command kubectl exec. OK, it is the just-in-time type of access. It means that the requesting team pushes the magic button, the request is raised, the request is then approved by the security team, and access is granted for the next 4 hours, let's say. And here we have two options, either to use the same logic providing the cluster-wide access, but in this case, we provide to SRE team this kind of elevated access to the security namespace, which we want to avoid. Or we should halt the idea of using cluster role binding and use many role bindings. In this case, if we have 100 namespaces in the cluster, it means that we have to create at least 99 role bindings. And in case of fusion namespaces, we need to implement some kind of automation. Like for any new namespace, we need to create this kind of role binding there. I prefer to use the option number 1. Let's see how we can implement this kind of deny rule. Just-in-time access is based on just an additional group added to the list of the groups which we have inside the user info section. So we simply take this group, we take the type of operation when the kubectl exec command is executed. This type of operation is called connect. And kind of object, this kind of object is created every time someone submits kubectl exec command. And the name of namespace and the combination of these fields, like we want to say to our policy agent that for any kind of request coming with these groups inside this namespace with this type of operation and with this type of resource should be denied. Which means that access control will be enforced on the next step. It will be allowed by role-based access control, but will be denied on the validation step, meaning that the policy enforcement point is different. But it completely fulfills our requirement, and it pretty works. The option number 2, it is the place where admission control can also help us. It is quite a wide approach to use admission request as a source of information to your custom logic. In our case, we say that we want to create admission request every time a namespace is created or updated. And then we submit this admission request to our custom logic that we have written using Golang, for example. You don't even have to write anything on your own. You can use already developed solution. It is the link to the Kyverna policy library. Even if you don't use Kyverna as your policy engine, you can sneak the logic from the policy. They have great examples and implement this kind of logic using your own policy engine. But in a nutshell, this policy and Kyverna will create neural bindings in newly created namespaces. So everything already developed. Another use case is role-based access control audit. I believe that the wildcards in the Kubernetes roles should be used only within this predefined cluster admin role. It is created by default. You do not have a lot of options to deal with it. Even if it is deleted after your kube API server is restarted, this role will be recreated. But again, you should avoid using this on your daily operations. On the slide, you see the report coming from Gatekeeper based on the following policy. Gatekeeper analyzes all the role bindings in the cluster, finds the references to the roles from these role bindings, inspects the roles, whether there are wildcards present in the role, and if it is the case, it sends me the subject from the role binding. According to the column number 3, we see that the cluster admin role is bound to a service account, which is an interesting case to be reviewed by your security department, at least. Starting from 28th version of Kubernetes, we have so-called validation admission policies introduced as beta. This is the direct competitor to external policy agents. But it has quite limitations, at least at the moment. For example, it is not possible to achieve the logic from the previous slide using web. Why? Because we saw some cross-referenced. It was implemented by Gatekeeper, and I said that initially, we start inspecting role bindings, and then we cross-reference to roles. And this is possible because Gatekeeper can use a cache, and we store roles and cluster roles in the cache. In case of Kyverna, you can submit external requests, for example, to Kubernetes API on the fly. Remember when I said that admission request is the main source of information for your admission decisions. So the limitation of web is that at least nowadays, web can only use admission requests, and nothing external can enrich those admission decisions. On the contrary, policy agents do allow you to do so. Let's say we have a shared cluster. Multiple teams work side by side. And most probably, you are not satisfied with the default Kubernetes networking model that presumes that any kind of pod is able to address any other pod by default. The same logic, we can create the default deny network policies when a new namespace is created. We can check the presence of the default deny network policy when a new workload is going to be created. So quite simple. But let's consider the scenario when you say, OK, developers, starting from tomorrow, you need to create network policies for your applications. Otherwise, all traffic to your applications will be dropped. Developers say, OK, boss, no problem, and create a network policy with this first line. This first line means that there are no limits. Any kind of egress traffic is allowed. Are you happy as a security guy with these kind of network policies? Probably not. But the requirement was fulfilled. The network policy was present. You can implement a basic linting of this kind of permissions. But here's the trick. We have a network policy in our YAML manifest. And let's take a look at the first two lines. They are similar in nature, meaning they provide limitless egress access. But what do we see regarding these two lines when we have an admission request and a JSON representation of the object that is carried in the admission request? We see that they're different. These two lines are similar, but these two lines are different. The trick is that there is a chain of unmarshalling and marshalling between your object descripted in the YAML manifest and how this object is descripted using JSON in the actual admission request. And I drop a link to a very nice tool. It is written by the Open Policy Engine developers. This tool takes an input as a YAML manifest of your object and gets you back a JSON representation of this object, how it will look like inside an admission request. So this tool can save you a lot of hours, believe me, if you want to implement this kind of linting logic. A really quick introduction to the scenario where we can use admission control for securing supply chain. Let's say we craft an image, we build it, we push the image into the OCI registry, we then generate a bill of material to this image. The bill of material is just a long JSON with a list of different software packages that can be found inside the image. You then sign this bill of material, and the combination of the signature and the bill of material itself is called attestation, and attestation is stored in the same registry just as another OCI artifact. We then have an attempt to create a pod. We have a policy engine in place. We have a special policy for the policy engine telling, hey, policy engine, please inspect the admission request of this pod. Take the image from the pod's manifest, find this image in the OCI registry, find the corresponding attestation for the image, reads the bill of material, finds whether there are some vulnerable packets present, and in case they are, please drop an attempt to create this pod. And regarding the signatures, the logic remains the same. It's even simpler, because signatures are also stored as OCI artifacts inside the OCI registry. You just check the conformance that your image is validated and signed. Yep, the logic remains the same. A couple of miscellaneous thoughts. We saw how we can use admission controls and policy engine to generate different resources. The same logic can be used for cleanup. For example, if you had orphaned config maps or secrets that are not used for a while by any pods, probably it is a good idea to remove them. We have a nice case when a development team uses Kyverna with its mutation capability for fulfilling their gatekeeper policies. And don't forget that checking the conformance of your custom resources, in case if you implement your own custom resources and custom operators, the cheapest way to do so is using admission control. And if you use KubeBuilder, it is, I believe, the most famous tool regarding crafting your own operators. It creates, in the skeleton of the project, admission control section by default, meaning it provides you with everything you need to create admission request and to be sent for your admission controller to be analyzed. That's it for the pitch. At this point, I hope I attract some of your interest to this technology. Now let's take a step back and see the main outcomes we have at Exness when we started to enforce the core of admission control, the pod security standards. The first finding, and it was quite expected, that majority of cases, majority of alerts come from these 4 lines in a manifest. I call them the bad defaults, obviously because by default developers do not use them, and the default values of the settings are not something that the security team will be satisfied with. running as root, dropping no capabilities. You got the idea. The great finding regarding this, and many thanks to our rigorous developers, was that we can find the bad defaults with good defaults. The idea is if that your application fulfills these two requirements, meaning that it doesn't need to be run as root user, it doesn't need to write anything to local storage, it is perfectly fine to wrap these kind of applications with these kind of good defaults. Even if your user ID used in the Docker file is not the same as the user ID used in the Kubernetes manifest, and by the way, the Kubernetes manifest take the precedence, you will ruin nothing, even if your user ID do not match, unless your application does not need to make a lot of writings or you have a really complex system of Linux permissions inside the image. We have our homebrew release platform. And for that platform, we introduced just a simple check mark where you can put a check if you want your applications to be wrapped with these good defaults. And this way, as a developer, you don't need to put these lines into your manifest manually. Probably the biggest finding was that the main problem, the biggest task dealing with pod security is to fulfill exemptions. What are our options here? First of all, try to check whether your third-party software already has a security context defined in the Helm chart provided you by the vendor. For example, recent versions of Argo CD do have the security context. We switched it on. It ruins nothing. Argo CD is up and running still. In case you don't have such luxury, you still can apply some magic to your Docker files. For example, for Nginx, native image taken from Docker Hub library, you can substitute the port 80 with the port 8080, for example, to avoid the need of using root user. You can implement empty tier volume types for the directories where Nginx need to write anything, and thus you simply can put a proper security context to the image, and it will work. We even have cases when some legacy software used to be run as privileged container, meaning that there is no security boundaries between this kind of container and a process running as a root user on the underlying nodes. We have great engineers, several lines of Golang code, and now this kind of service works pretty fine with a proper security context and sends 0 alerts to the security team. But for some kind of services, it is not possible to refactor them. For example, Istio sidecars. They need to apply some magic to the underlying host networking. I found that it is profit to have a general way to provide exemptions across a wide variety of the policies. And I found out that a combination of an image and namespace works pretty fine in most cases. For example, if you use kubespray, you know that inside the kubesystem namespace, there is a native installation of Nginx taken from Docker Hub library. This installation works under root user, using the host network, and relying on the host pass volume, meaning that if we exclude these 3 policies using just an image, it understands that any kind of user with permissions to run pods is able to run this image and bypass these 3 policies across all the namespaces. But if we add a namespace to the equation, it means only within the kubesystem namespace now it is possible. And should your developers have an access to kubesystem namespace? Probably not. Some policies will require to have exclusive settings for providing exemptions. Restrict host passes. Getting back to the previous example, we said that our kubespray Nginx installation does rely on host pass. If we exclude just a combination of an image and a namespace, it means now it is possible to run this kind of image in this kind of namespace using all kinds of host passes. For example, mounting the whole root directory from the underlying node to the container, meaning that your node is already hacked doing so. If we provide something like a list of allowed passes, we say that it is impossible to use only the passes from the list. Probably it's a good idea to add additional setting here, like the path should be read-only or not. OK, now we have dozens of policies, hundreds of exemptions, and we need to propagate all of these goods to our clusters. Here we're getting closer to another fancy terminology nowadays that we have. I mean, policies as a code, which is tightly connected to infrastructure as a code, which is tightly connected to GitOps approach, which will be described in the details my colleague, Alexander Surgurov, at this hall 2 at 2:40. Highly recommended. Sorry for this kind of aggressive marketing. So policies as a code. Our infrastructure model, current infrastructure model, presumes that we have a relatively large amount of relatively small clusters. And as a security guy, I need to propagate dozens of policies with hundreds of exemptions across dozens of clusters. Of course, it is not feasible to do manually. I need to rely on some delivery tool. It's not a problem. You have plenty of options to use delivery tools for cloud-native infrastructure, but it's just a part of an equation. The other part is to use templating. Helm file is one of the tools we use to propagate something across clusters. And I use Helm file to propagate my policies. I wrap them as Helm charts. If you're familiar with Helm chart structure, you understand that there is the values YAML file, and it serves as a storage for global variables. When I need to apply policies to cluster A, I just run the Helm file and provide some specific settings inside the values YAML file suitable for cluster A. Then I repeat the procedure for cluster B, C, D, and so on, meaning that everything I need to change is unique values. That's it. Another good finding that you will be breaking the habits of your developers, of your release engineers, any other users of Kubernetes by introducing this security enforcement. For example, when you start enforcing a root file system to read-only mode, you will start encounter questions from developers. Hey guys, I'm not able to get a shell into the running container and download curl of get to the running container, which, of course, kind of disaster for our security operation guys. Every time they listen to such kind of questions, they scratch their heads, but it was quite common practice in case of firefightings. You will see that those curls, vgets, and kubectls are now propagated across base images. And this is another problem for a security department, because obviously these kind of tools significantly broadens the possible attack vector. If container is already compromised, these tools will be used to elevate the privileges and to execute lateral movement, obviously. But again, we saw examples how we can use admission control to check bill of material for images, or to control kubectl execs and attach and debugs and any other kinds of ways to get an actual shell to the running containers. There is a ton of other pretty interesting technical material I would be happy to share with you, so reach me out if you want. But the main point that I want to highlight here is an organizational point. Admission control, if being properly implemented, is a full-fledged control with all the consequences you have here. And I mean the day-to-day routine for your security department. For example, probably you should have an interface between developers and the security team. If a developer needs an exemption for some kind of third-party software which is impossible to refactor, or which we understand that it's not feasible to refactor, you better have some kind of service desk template where developer can raise a ticket that will be approved by security team or rejected. You will not be trying to implement admission control in deny mode from the beginning if you're not quite OK having your production out of service for weeks, for example. You will start with audit. You then will probably be switching to the warning state, then to deny state. And each of the changes between states should be scheduled. They should be told to your developers and release engineers. And of course, you should propagate the expectation, your expectation as a security team to developers, why they should start to implement all kinds of run as user, run as group settings across their manifests if they did not used to do so. This is the slide where I need to spend some time telling you that security is a layered approach, there is no silver bullet, and any kind of very boring but very true information. Admission control, I believe, is the most capable control when we're dealing with the events coming through Kubernetes API. But of course, it helpless against events happening outside the cluster. For example, a direct manipulation with container runtime or etcd backup compromises. It's obvious, layered approach, as usual. Bear in mind that the best friend of admission control is role-based access control, and vice versa, as we saw previously. For example, there is kind of attack on admission policies. If you are able to read the admission policies, you are able to read the logic of exemptions, meaning now at least you understand what you should do to bypass the policy. And I drop a link to the admission control threat model. It is a nice article created by the Kubernetes security SIG group. And it describes admission control as a vector attack, not as a control. So recommended to take a view. And probably that's it. Thanks for the attention. If you have any questions, you can send them to my secretary. Of course, I'm joking. Let's discuss them.
Thank you. Thank you, Roman, very much. Please don't forget to rate the talk over here. Yes, I see at least one hand. Don't be shy. We have a special present. For the best question asked, please here to the left. OK.
Thank you so much for your talk. I have a question. Let's imagine we have a big enterprise with 20 years plus history, with lots.
Don't be shy and put the microphone closer to your mouth.
Yeah, thank you. So we have a big enterprise with lots of legacy, with lots of infrastructure, cloud native, bare metal, some providers, and so on. And can you share some efficient communication strategies and tips and tricks how to force the company to use the novel technologies and go back from the legacy code, and what problems maybe you encountered during this journey, and maybe you can help others to achieve the same? Thank you.
Two tools I found useful in this scenario. The first one is repetition of a repetition of a repetition of a repetition. Enormous amount of repetition that we're going to enforce this, why we're going to enforce this, and this is the key. Another one is, first of all, a good understanding why you're going to provide this kind of enforcement, and the ability to convey the need of the technology to the guys that will be affected by the technology you are going to enforce. I would say these two organizational points is a key.
Thank you. Another question here to the left, please.
Thank you for your presentation. Speaking about shift-left approach, are you validating your developers' manifest before deploy stage? For example, during GitLab pipeline is working?
Yep, it's possible. First of all, the policy engines I mentioned during the slide deck do have an emulation of the work as admission controllers, but during the ICD pipelines. Yep, the general question is yes. The decision you make, either what kind of stress you want to put on the CI/CD cycle and what kind of stress you want to put at the admission control point, well, it is discussable. It depends on your needs. But the short answer, it is possible. Yes, we do so. Mm-hmm. Some teams are quite fine using the Gator CLI. It is an emulation of GitKeeper for their own needs. I mean, we do not propagate, we do not enforce the usage of this tool, but they found that it is profitable for them to try to inspect the images before they come into Kubernetes in case to not face an unaccepted denies from the admission control step.
Mm-hmm. And the second question, maybe I missed something during the presentation. Do you enforce security context for your developers, or you just recommend them?
We are enforcing them, yes. But again, the cycle is pretty known. Audit, warning, then only deny when a team is fully prepared, and it will not be a surprise for them to switch to the block mode or deny mode, sometimes reference.
And about deny mode, are you working in fail-safe mode? So for example, if something is wrong with your admission controller, with Governor or OPA, will the deploy be successful?
We use ignore mode, and I feel it is more safe approach in case you monitor the presence of validating configuration. You got the idea, yep?
Yeah.
If it is failed, your requests are passed by default. It is failed when you have problems with your admission controller. Either it is not working, I mean the pods are not running, or you don't have a validating configuration or mutating configuration in place. So you check the presence of validating configuration, and you check the health of the admission controller itself. I believe this combination of 3 points is more safe than to use the failed when your requests are failed, when admission control is not reachable.
Thank you. We have a question over here to the right.
Hi, Roman. So you mentioned that you resolved some issues with legacy privileged services with some middleware written in Golang. Could you please tell a bit more about how you resolved it? What magic does the Golang code to, as I understand, seamlessly run legacy services without changes in them?
This particular case, it was a container with a cron job. This cron job used to mount an SMB volume. And the general way to mount an SMB volume is to have any kind of, quite high permissions to do so. In case of containerization, this service was crafted in a way that it used to work as privileged one. Our release engineer that was responsible to this service found a way to use a Golang package for working with the sieves and SMB directories. And this Golang package provides everything you need in the user namespace, meaning that you do not need to rely on the sysadmin capabilities like it was previously. And it was the trick. It solved the problem. Now it works pretty fine with dropping all the capabilities and working just.
OK, so it's not a silver bullet. That's just for a specific case.
Yes, it's not a silver bullet. Okay. It was just a case. But my point on that slide was, in some cases, it is possible. In some cases, unfortunately not, and you need to deliver exemptions.
Yes, please, here.
Hello, thank you for your presentation. There was an example how admission control may help you to prevent start pods with vulnerable versions of dependencies. And I have a question: why do you deny starting pod container instead of denying pushing Docker image to Docker registry with vulnerable dependency?
Layered approach, etc. In case you already have a ton of different images in your OCI registries, it can be an option to go with. Of course, it is cheaper to block an attempt to pull the image using the OCI registry, yes, and it is the first line where you should think about this kind of control. But again, getting back to this example, you don't have to put the deny mode on these rules. And personally, I feel that it provides you more profit when you use this kind of control as an audit. Let's say tomorrow we know that a new version of OpenSSL is vulnerable. How do you want to find any cases of this software package be used inside your running containers? You can put this kind of policy in the audit mode, run a couple of cycles of auditing, and you have a report that to this, to that, and to those images, this kind of vulnerable package is used, and these containers are already running in the cluster.
Yeah, it makes sense. Thank you.
Thank you. Another question here to the right.
Hi. Where would you define the line between the physical infrastructure security and the Kubernetes? What is the best way to approach from a sysadmin network security aspect? And
this line is invisible, unfortunately.
That is the big question, yeah.
The first candidate to act as a bridge between these two sections is runtime security, probably. By runtime security, I mean the software that is aware of what's happening on the underlying node. For example, Tetragon, Falca, all these guys that can analyze these calls, for example. Why this can act as a breach? Because they have a cloud-native installation, Kubernetes native installation, meaning that you can rule them using Kubernetes API, and you can ingest the information that they submit to you using Kubernetes logs, for example, delivering using your Kubernetes native stack of logging. And you mentioned Kubernetes security, the same approach. If you have CNI capable of dealing with network security, you do understand that when you create a network policy, you are creating some IP tables rules under the hood in case your underlying node relies on IP tables. In case of eBPF, the same logic. You just create a Kubernetes abstraction, but you impact your underlying node's eBPF configuration. I mean, the breach is that the tool running as a Kubernetes native tool provides you a Kubernetes native interface to deal with the infrastructure configuration.
Thank you. We have a question over here, and please keep your hands so I can take a note with you.
Hello, my question about admission controller. For your opinion, what way is better? Deny, create, or update object in Kubernetes on validation webhook, or enforce it, set, valid data, and create object?
Could you please repeat the second part? You mean deny before the Kubernetes?
My question, what we must do? Deny by validate webhook, or enforce it, set, valid data, and create object?
Sorry, didn't get the idea.
Можно, может быть, по-русски?
Можно.
Мой вопрос вот в чем. У нас есть валидационный веб-хук и мутационный. У тебя в презентации было, что security контекст ставится через мутационный веб-хук принудительно. Ты считаешь, что это правильный путь или правильнее, если к нам пришло событие на создание объекта с неправильными данными, его заденаить? Или все-таки мы захотим принудительно поставить нужные нам данные и создать объект?
Yep, the question was about probably it worth to use mutation to enforce security context and other kind of relevant settings. It highly depends on the context of your CI/CD cycles and the ways your release engineer team works. Using mutation in case you already have a release platform may go wrong in many cases. You will have a lot of intersection between your release platform and between your mutation cycle. If you do not have a release platform at all, it can be a solution. And as I saw, we have a team that is quite comfortable of using mutation webhooks on their own to fulfill the policies that we enforce. I mean, my question is, again, there is no silver bullet. It is based on the process. If your process enables you to do so, I see no big troubles. But be cautious, because mutation, it is when the intended state is different from what a developer submitted. And in case your cycles are dependent on the intended state, which was committed in the GitOps, for example, and you then mutate them on the admission control, do be prepared to expect some unexpected events.
Okay, thank you.
Thank you very much. I think we're done with questions. We have only 1 minute left. So please, Roman, you had plenty of questions to choose from.
To the guy from the first line, because I do understand the idea behind this question. It's always great to have a silver bullet, and if we had a way to refactor all kind of legacy services to be capable to work in deny mode, it would be great.
Thank you, thank you. Please, round of applause for our brave hero. And another round of applause for Roman. Thank you very much. Thank you. You can catch him in the hallway and discuss everything you want.